The global internet depends on a physical network of fiber-optic cables laid across the seabed. Around 1.4 million kilometers of these lines connect the continents and carry roughly 99% of all intercontinental data traffic. In the deep ocean, a cable measures about 25 millimeters in diameter, no thicker than a garden hose. Inside are glass fibers protected by a copper conductor, polycarbonate insulation, and a steel strength member. Despite this small profile, modern space division multiplexing allows a single line to transmit more than 250 terabits per second, far exceeding satellite capacity. Maintaining that flow across the abyssal plane requires a specialized chain of hardware known as the wet plant. As optical pulses travel through glass fibers, light gradually weakens. To offset this loss, erbium-doped fiber amplifiers are integrated into the cable every 60 to 100 kilometers. These repeaters sit inside sealed, pressure-resistant housings. Within them, erbium-doped fibers are energized by internal pump lasers, amplifying the signal entirely in the optical domain. No electrical conversion takes place during transit. The housings are rated for depths of up to 8,000 meters. Continuous operation depends on a steady external power source linking the submerged system directly to land-based infrastructure. Power is supplied from cable landing stations using dedicated power feeding equipment. A constant current of high-voltage direct current, often reaching 15,000 to 18,000 volts, is injected into the copper conductor that surrounds the fibers. This layer functions as a single, uninterrupted delivery line across the ocean. Stations at both ends of the route typically share the electrical load. If one station goes offline, the other increases output to maintain the voltage required by the repeaters. This high-tension environment supports global data transmission, while also increasing exposure to physical disruption in active maritime regions. A live high-voltage line on the seabed introduces risk from both human activity and natural forces. Continuous operation depends on a combination of physical protection and automated oversight. In waters shallower than 1,000 meters, cables are buried 1 to 3 meters beneath the seabed using sea plows. This reduces the likelihood of contact with anchors and fishing gear, which account for most recorded faults. Distributed fiber optic sensing systems monitor the fibers in real time, detecting vibrations associated with nearby vessels. When a break occurs, network operations centers reroute traffic through alternative cable paths using mesh networking. A fleet of roughly 60 maintenance ships remains positioned at ports such as Brest and Portland to carry out repairs. Individual failures are contained, so the wider network remains active. The physical journey of transoceanic data ends at the beach manhole. This concrete structure marks the technical and legal boundary of the subsea system. At this point, international maritime regulations transition to domestic property and infrastructure law. Undersea-rated fibers are spliced into standard terrestrial backhaul cables. The signal leaves the high-voltage environment of the wet plant and enters submarine line terminal equipment, where optical wavelengths are separated and converted into standard IP traffic. This junction defines the mechanical limit of the subsea network. Beyond it, data moves into land-based transit systems. The global subsea network operates continuously. At any moment, trillions of light pulses move across the ocean floor, sustained by high-voltage currents and unattended repeaters. Monitoring centers remain active. Maintenance fleets stay on standby. Data continues to pass through beach manholes and into terrestrial networks. The system remains in place, functioning quietly beneath the surface of the modern landscape.